when we're working in vector spaces, we'll often need some way to say that you can somehow combine some vectors to produce another vector. And the language that we'll use for that is linear combinations. So when we're in a vector space, a linear combination of some vectors, v1 through vn, will be just some scalars times each one of those vectors, and then you add them all up. So here we say that v is a linear combination of v1 through vn. Right? This sort of combination is often something that we've needed to write down. So for example, in the vector space of 2x2 matrices, let's write this matrix, 1 minus 2, 3 minus 1, as a linear combination of all of these other matrices. So what I'm suggesting here is that we should be able to come up with scalars here to multiply each one of these matrices and produce the matrix on the left. Right? So to demonstrate that the matrix on the left is a linear combination of all of these matrices on the right, we just have to choose appropriate coefficients. Now in general, finding appropriate coefficients might be tricky, but for this example at least, finding what these coefficients should be is actually going to be pretty straightforward because, if you imagine putting some scalar in this first spot, what effect does that have on the matrix on the right-hand side once you add everything up? Well, whatever scalar we put here, say a1, it's going to multiply this one here, but then none of these other terms over here are going to contribute anything to this upper left entry because their scalars are all going to get multiplied by 0 in the upper left entry. So this a1 is the only thing that's going to affect the upper left entry. And what do we want this upper left entry to be? Well, we want it to be 1. So let's put a 1 right here. And similarly, you can see we should put it -2 right here to arrange for that -2 to show up. And we should put looks like 3 right here to get that 3 to show up. And then we should have a -1 right here. All right. Now, I won't go through all of the arithmetic, but if you want to, you can check that if you do all of the operations on this expression on the right-hand side, you do indeed get the matrix 1 minus 2, 3 minus 1. And so this matrix is a linear combination of these other 4. I'll just write those 4. I don't want to write out all of these matrices again. All right, so expressing one vector as a linear combination of some others is just a matter of choosing the appropriate coefficients so that when you actually put this linear combination together, you get the thing that you were supposed to get. All right, for another example, let's show that all vectors in Rn are linear combinations of these vectors. So what I'm trying to express with this pattern here is that we have n different vectors, and each one of them is all zeros except for one spot, which has a 1 in it. So E1 has a 1 in the first entry, E2 has a 1 in the second entry, E3 has a 1 in the third entry, and so on, down to En, which has a 1 in the nth entry, which is the last entry. So how could we show that every vector in Rn is a linear combination of these? Well, what does any vector in Rn look like, right? Whatever we write down for our sort of target vector, it has to be able to represent any vector in Rn. But to do that, I guess we have to have, variables for each entry, because we can't specify any of these entries because not every vector, if we actually chose a number for any of these, not every vector in Rn would have that number in that entry. So we have to have general variables for each entry. All right, so again, to express this as a linear combination, we have to choose coefficients for all of our e's. So let me just write E1 plus, choose some coefficient, E2 plus, so on down the line. We need to choose some coefficient, times En. So what do these coefficients need to be? Well, you know, this example is actually a lot like the previous example, except we have all our numbers written as columns instead of as a square matrix. But it's the same idea. There's a 1 only in one spot, and everything else is 0, right? Each one of these vectors only has one entry that is non-zero. So whatever scalar we put in front of, say, E1, that is the only scalar that will affect the first entry of this linear combination. And we want that first entry to be A1, so we should put A1 right here. But that means we should put A2 right here, and so on down to AN. Okay, so this shows that every vector in Rn is a linear combination of just these n vectors. All right. Finally, one last question about linear combinations is in P3, remember this is the collection of polynomials of degree less than or equal to n. Sorry, less than or equal to 3. Is the 0 polynomial a linear combination of x, x squared, and x cubed? So the 0 polynomial, I guess we could write that as just 0. Is it possible to write this as some scalar times x plus some other scalar times x squared plus some other scalar times x cubed? So is it possible? Well, at first you might think no, because whatever numbers you put here, you're going to have some x's on the right-hand side, and that means it won't be equal to 0. But if you go back to the definition of linear combination, we just said these scalars have to be real numbers. 0 is a perfectly good real number. So if we chose the scalar 0 for all of these, then on the right-hand side, we do get 0. So yes, it is possible to write the 0 polynomial as a linear combination of these 3 polynomials. The point of this example is just that we have to remember that choosing 0 for a coefficient is a perfectly valid choice, right? What this is telling us is that to produce 0 as a linear combination, we didn't really need these polynomials. We could have done it with fewer polynomials. In fact, we could have done it with no polynomials, right? But having a 0 coefficient in a linear combination just tells you that you didn't really need that vector to begin with. All right. Of course, for all of these examples, I've cooked these up so that coming up with the appropriate coefficients is pretty straightforward. We can just kind of look at it and guess. But that's often not the case. So what if we wanted to express some more complicated vector as a linear combination of other vectors? So how could we do that? Well, what would a linear combination of these 3 vectors look like? Well, it would be some coefficients, some scalars, so a1 times -1, 0, -1, plus some other scalar times 2, 1, 2, plus a third scalar, a3, times 4, 3, 3. And we want to know, is it possible to choose scalars so that this is equal to -6, -2, -6? Okay. Well, it's not at all clear if this is possible, but if you look at this just right, this is actually a linear system of equations. So if you look across just the first entry of all of these things, going across the first entry, we get -a1 plus 2a2 plus 4a3 is supposed to be equal to -6. And then going across the second entries, we get 0 times a1 plus 1 times a2 plus 3 times a3 equals -2. And just to be complete about it, I guess I'll finish writing it out. -a1 plus 2a2 plus 3a3 is equal to -6. Look, this is a linear system, right? With 3 unknowns, a1, a2, and a3. So we already know how to solve this linear system. Just write down an augmented matrix representing this system, and then do row reduction. In fact, when we write down the augmented matrix for this system, -1, 0, -1 down the first column, and then 2, 1, 2, 4, 3, 3, and then -6, -2, -6 in our augmented column. When we write down this augmented matrix, look, the vectors that we started with are making up these columns, and the vector that we're aiming for is the augmented column. So, now that we know this, finding coefficients to express one vector as a linear combination of other vectors, it's just a matter of solving this linear system. So we've done this a million times, so I'll skip straight to so I'll do row reduction sort of off camera and write down the reduced row echelon form right here. Okay, so here's the reduced row echelon form for this matrix. And remember, we can translate this directly into values for A1, A2, and A3. So A1 has to be 2, A2 has to be -2, and A3 has to be 0. Right, so what this is telling us is if we go back up here and we put a 2 here as this scalar multiple, I can't get colors right now for some reason, and a -2 for this scalar and a 0 for that scalar, we ought to get -6, -2, -6. So -2 -4 is -6, yes, 0, and -2, -2, and then, yes, it works. So expressing one vector as a linear combination of others is really just, when you get right down to it, it just comes down to solving a system of linear equations, which with row reduction, we already have a good tool to solve this kind of problem.